In this video, we're going to learn about a completely new kind of number, a complex number. Now you might ask yourself, why do we need a new set of numbers? We're going to be examining a class of equations called quadratic equations. Sometimes those equations don't have real number solutions. Complex numbers allow us to extend the real number system so that every quadratic will then have solutions. When mathematicians started trying to solve quadratic equations, they noticed that often they were required to take the square root of a negative number. Now we know that if we multiply two negatives together, we get a positive number, and if we multiply two positives together, we get a positive number, which means that if we only use real numbers, we can't take the square root of a negative. In order to get around this, mathematicians came up with the number that we're going to denote with the letter I. I is going to equal the square root of -1. That means that when we square I squared is equal to -1. Complex numbers then are going to take the form A plus BI. When we write a complex number, the number A is a real number, and that part of the complex number is called the real part. B is also a real number, but it's getting multiplied by I. So the part of the number that we write as B times I is called the imaginary part of that number. We'll see when we're simplifying complex numbers that we're going to treat the real parts and the imaginary parts the same way that we treat like terms when we're simplifying algebraic expressions. Let's take a look at a few examples. Let's start by simplifying some numbers that involve square roots of negatives. So here we have the square root of -9. We know that the square root of +9 is equal to 3. We also know that the square root of -1 is going to be this number I that we're using for complex numbers. So we can rewrite the square root of -9 as the square root of -1 times the square root of 9, and that gives us I times 3, which we'll write as 3i because that's traditionally how you write a complex number. And notice that that is the same as the complex number 0 plus 3i, where 0 is the real part and 3i is the imaginary part. Let's try the square root of -20. Well, that one doesn't have a nice perfect square root, but we're going to do something similar here. We're going to rewrite this as the square root of -1 times the square root of 20. This is I. The square root of 20 is the same thing as the square root of 4 times the square root of 5. Now I made that choice because 4 is a perfect square, which means that I can rewrite this as I times 2, that's the square root of 4, times the square root of 5. We're going to rearrange that again to put the I at the end. So we have 2 square roots of 5 times I, which is the same as the complex number 0 plus 2 root 5 times I. 0 is our real part, 2 root 5 times I is our imaginary part. Now we don't generally have to write the 0 when we're talking about complex numbers. We can usually just leave that off and write the number as 2 root 5 times I. Here we have the square root of 4 the square root of -4 times the square root of -25. We cannot, when we have two negatives inside the square roots, we cannot just multiply this and get the square root of 100. Let's take a look at why. The square root of -4 we can rewrite as 2 times I. That's because this is the same as the square root of -1 and the square root of 4, which gives us 2i. Similarly, the square root of -25 is 5 times I, because this is the square root of -1 times the square root of 25, which is 5 and I. When we multiply those together, we get 10i squared. Remember that I squared is equal to -1. So that means that this is the same as 10 times -1, which is -10. If we had just started by doing multiplication, so let me show you the wrong way to do this. If we had multiplied those together and gotten the square root of 100, we would have gotten +10, which is the wrong answer. So we have to simplify first and then multiply together. We're going to do something very similar in the next one. Here we have the square root of 98 over the square root of negative 2. I'm going to simplify those individually. So 98 is the square root of 49 times the square root of 2. On the bottom, I have the square root of negative 1 divided by, or times the square root of 2. The square roots of 2 cancel because the square root of 2 divided by the square root of 2 is equal to 1. And so I have the square root of 49 over the square root of negative 1, which is 7, divided by I. Along with simplifying complex numbers, we can also combine them using the typical operations we use for real numbers: addition, subtraction, multiplication, and division. Here we're going to remember that we're going to treat the real parts and the imaginary parts as like terms. So in other words, when we look at this first problem, 16 minus 3i, that's our first complex number. And then 3 plus 5i, that's our second complex number. Each of those has a real and imaginary part. We're going to combine the real parts and we're going to combine the imaginary parts. So first thing I'm going to do is I'm going to notice that this negative number belongs to both parts of my complex number. So I'm going to go ahead and distribute it. So this is going to become 16 minus 13i minus 3 minus 5i. And now we think about our like parts. So we have a 16 and a negative 3. Those combine to give us a positive 13. And then we have a negative 3i and a negative 5i. Those are going to combine to give us a negative 8i. This is the new complex number. The 13 is the real part, and the negative 8i is the imaginary part. And they come from combining the real and imaginary parts of the original numbers. Our next one involves multiplication. So we're multiplying negative 4 minus 3i times 2 minus I. We're going to use FOIL, or the distributive property, in order to do that. So I'm going to do negative 4 times 2. That gives me negative 8. Then I'm going to do negative 4 times negative I. The two negatives combine to give me a positive, so I get positive 4i. Then I'm going to do negative 3i times 2. I get negative 6i when I do that. Then last, I do negative 3i times negative I. Again, the two negatives combine to give me a positive, and I get 3, and I get I squared there. Now, we want our final answer to be a complex number. We need to write it in the form a plus bi. So now we have an addition problem and subtraction going on here. So we're going to combine our like terms. Before we do that, let's look at this last term, 3i squared. Remember that I squared is equal to negative 1. So in other words, we could rewrite this expression as negative 8 plus 4i minus 6i minus 3. So now our real parts are negative 8 and negative 3, which is going to give us negative 11. Our imaginary parts are 4i and negative 6i. That gives us minus 2i as our final answer. The next one's similar. We have to remember that squaring means multiplying a number by itself. So we're going to write this as 6 minus 7i times 6 minus 7i and use the distributive property. We cannot just do 6 squared minus 7i squared. That does not work. We have to remember that squaring means multiplying the entire thing by itself, and we have to use the distributive property in order to do that. So again, just like above, we're going to do 6 times 6. 6 times negative 7i is negative 42i. Again, we have negative 7i times 6. That's another negative 42i. And then lastly, we're going to do negative 7i times negative 7i, which gives us positive 49i squared. But we're going to remember again that I squared is equal to negative 1, which means that this term becomes negative 49. So if we rewrite that, we have 36 minus 42i minus 42i minus 49. Our real terms are 36 minus 49, which gives us negative 13. Our imaginary parts are negative 42i and negative 42i, which gives us a negative 84i. Our last example is again a multiplication. We have 2 minus 5i times 2 plus 5i. These numbers are what we call complex conjugates. Complex conjugates are numbers that are of the form a plus bi and a minus bi. And we're going to see something that happens when we multiply these out. Again, we're going to use the distributive property. So we're going to do 2 times 2, 2 times 5i, negative 5i times 2, and negative 5i times positive 5i, which is negative 25i squared. Again, we use the fact that I squared is negative 1 to notice that this term is the same as positive 25. So we get 4, then we have plus 10i, minus 10i, plus 25. And that, if we combine our real parts, we get 29, and if we combine our imaginary parts, we get 0. So notice we just got the number 29, which is a real number, and that will always happen. When we multiply complex conjugates, we always get a real number, and that number is going to be a squared plus b squared. Notice that 29 is the same thing as 2 squared plus 5 squared. All right, so wrapping up what we've learned here, we see that complex numbers complete the number system. What that means is that they provide solutions to equations that aren't available when we only use real numbers. When we work with complex numbers, the real parts and the imaginary parts are treated the same way we treat like terms in algebraic expressions. We're going to use the fact that I squared is equal to negative 1 to simplify and perform operations on our complex numbers. We'll see eventually that complex numbers appear naturally inside of what we're going to call quadratic equations. So up next, we'll start with learning how to solve quadratic equations and finding out how we can make these complex numbers useful for us.